Hello, my name is Stephan Garcia, and today I want to talk to you about drag forces. A drag force is a mechanical force that occurs when an object and a fluid are in contact with each other but have a difference in velocity. And a fluid means any gas or liquid. It's sort of like a friction between the molecules of the fluid and the surface of the object. So the force of drag on any object is going to be opposite to the direction it's moving. And if you have trouble picturing that, then imagine you're roller skating down a hill. So at the top of the hill, it feels like there's no wind, it's a very nice day, but once you start going down the hill and building up speed, it feels like there's a ton of wind against you, and that is called air resistance, which is a type of drag force. So the magnitude of that force is proportional to a few things. A coefficient of drag, which is different for every object, the density of the fluid, which is like, since the fluid could be either a liquid or a gas, that if you pass through water, which is much denser than air, you'll slow down a lot more. Then we have the area of the object, which is really the surface area. So if you have a man skydiving, before he opens up his parachute, he's going at a very high speed. But once he opens it up, he's expanding his surface area. So more air is colliding with him. And that will increase his drag force and slow him down or decelerate him. And since drag force, just like any other force, is equal to mass times acceleration, he slows down very quickly. The other thing that drag force is proportional to is velocity. The reason for that is that, say, if you're just standing still, there's no resistance against you from the air. But like I said before, if you're going down a hill or any other thing at a very high speed, that's when you'll feel the resistance. So that's why velocity comes into play. So all of these can be modeled into an approximated equation. Force of drag is equal to 1/2 the coefficient of drag times density of the fluid, the area, and velocity squared. Now, this is an approximated formula, but all of these, coefficient, density, and area, those are all constant throughout the problem. So you could also look at it as force of drag is equal to a constant, which we'll call B, times V squared. But V squared only works in some cases. Like I said, this formula is approximate, so sometimes it's more accurate to portray this formula with just a V, which makes things simple for calculations also, and it's usually a very close answer. So say you have an object falling. It has some mass, of course, and the first force on it is gravity, so the weight of the object is mg. And then the drag force, which, since the object is falling, will be in the opposite direction, up, which we'll say is equal to bv. So these are both of our forces, so if we want the net force on the object, we just have to subtract them since they're in opposite directions. So the net force is equal to mg minus bv. So what does this mean? Well, a net force is still equal to mass times acceleration. So this will be the total acceleration on the object. So after a certain amount of time, this force and this force, the drag and gravity, could become equal to each other if the object has reached a high enough speed. And when that happens, since if these are the same force, this will equal to 0. So 0 equals mg minus bv. But at that point, the velocity will no longer change since there's no acceleration. So that is what we call a terminal velocity, which is different for each object. So this is the okay. So this is Vt, T for terminal. So if we wanted to solve for that, all we would have to do is move this to the other side by adding bv to both sides. So v times terminal velocity is now equal to mg. And then all we have to do is divide by v, and we have our terminal velocity. So all we have to do is divide by v, and now we have our terminal velocity. Mg over v. So what does that mean? Well, over here, we have a graph of velocity versus time, or well, just the axis. I'll show you the graph in a minute. So if this is our terminal velocity right here, that means that over time, if we drop the object at rest, the initial velocity where it starts on the graph will be 0. So it'll start at the origin, and it'll go up and up and up. But then as it gets very close to this will be like an asymptotic line. And the velocity will go like that. So this might not be the best drawn graph, but if you want to see a more accurate representation of it, the formula for this, using this approximation, would be the velocity as a function of time is equal to the terminal velocity times 1 minus e to the negative bt over m. And the way you arrive at this involves some calculus, because this, since acceleration is the derivative of time, can be rewritten as m dv over dt. And that's still equal to mg minus bv. So if you really wanted to, and you know calculus well enough, you could move the v's to one side, the rest to the other, and use some integration and come up with this formula. So if you know calculus, I encourage you to try this, and I'll give you the start of it. So if you really want to try this at home, integrate from 0 to v with 1 over mg minus bv times dv, and from 0 to t with 1 over m dt. And all I did to get that was multiply both sides by dv, divide by this whole thing, mg minus bv, and divide the m from both sides. So that's how you get to here. And if you know calculus, it'll involve some u substitution. So if you're familiar with it and comfortable, I encourage you to try it. So thank you for watching, and I hope you find this as interesting as I do.